Alright, so let's continue. For example 1.8 shown in the slides, we want to find out the electrical charge provides with an infinitely long line charge. Well, the problem is a little bit not that practical. However, it's a practical assumption, because for long lines, the electrical field established from a long line can be approximated as the field produced by an infinitely long line, even though that is the concept seems a little bit complicated, but the computation can be simplified based on this assumption. And the result is quite useful. It's quite useful for treating electromagnetic problems. So suppose we have a very long line, infinitely long, and we have a charge line, a charge distributed on this line. Well, not a current. The electrical source on this line is electrical charge, pretty much like a string of hair and with some charged particles on it. So be careful, this is not current, because currents shall build up magnetic field, while charge shall build up electrical field. So here we are talking about electrical field. So we are talking about electrical charge distributed on a line. All right? So to simplify the geometry of the problem, we place this infinitely long line on the z-axis. So as you can imagine, what kind of coordinate system is more suitable for this problem? Well, I'll leave it up to you. Okay. All right. So anyway, as the figure shows, the charges are distributed evenly. Are distributed evenly on the z-axis. That is the red vertical line on the plot. And of course, the first step in treating this problem is divided the line charge into short pieces. So we divide it into many small sections. And as the plot suggests, or as the plot remarks, we have two sections. One is above the horizontal plane, and the other is below the horizontal plane. As you can see, they are symmetrical ones. So we have a pair of vertical sections on top and below the observation point. So the observation point is placed over here. The coordinate of this point is x, y, 0. Note that the z-axis of this observation point can be chosen as 0, y, because the line is infinitely long. So it extends upward and downward infinitely. So you can recalibrate the coordinate systems as, well, the z-axis of my observation point is 0. Well, just recalibrated. 等于重新校正你的位置了，因为这一条线它是这个 source 线是往上往下无限延伸的，就像说，我的位置是什么？我的位置就是宇宙的中心啊，看你要怎么定义那个 coordinate system 嘛，对不对？所以这句话是没有错的，OK， so just so because the line is infinitely long, so it's convenient to align this observation point to z equal to 0. Okay, so as you can see here, they are of symmetrical position for the for this pair. So on the top is 0, 0, z prime, and below it is 0, 0 minus z prime. So using the Coulomb's law, you can write up the electrical field from the line source above and below the horizontal plane. There are 4 pi epsilon sub 0 times r to the square plus z prime to the square y. This parenthesis provides you r to the square, the distance from observation point to the source. And due to the symmetry in geometry, so the source above and below the horizontal plane have the same distance, which is r to the square plus z to the square. Okay, and the amount of charge is this. This is q, which is the product of the length of the section, which is dz prime, times rho L sub 0, that is the line charge density of this infinite line. Okay? The second thing is take advantage of the geometry of the problem. As you can see, the direction of electrical field should pointing along this line as this black arrow, which is pointing downward over here. And the electrical field built up by this section should be this black arrow. And due to the symmetry of the geometry, the 2 black arrows can be decomposed into vertical one and horizontal components. So as the figure suggests, the vertical projection of the 2 black arrows are, what happens to them? They cancel each other because they are of opposite direction and of the same magnitude. So the vertical components cancels, while the horizontal components remains. That is the red arrow as you see here. So the summation of the pair of the 2 sources can be written as 2 times cosine alpha, while cosine alpha can also be found using this geometric relationship, that is r to the square plus z to the square divided by r over this thing, right? So we can derive this formulation for this from this geometry. Then what next? Well, the next step is to add up all the fields from each pair on the line. Okay, so here are some more tricky part, right? So as we seen from the previous slides, because due to the symmetry of the 2 charge sections, we only have AR components, that is the projection on the XY plane. And they can be returned, the formulation can be returned using the geometry provided by the problem. So here's the expression for cosine alpha, all right? So that's pretty much the result we have in the previous slides. Okay, so these slides summarize the solution of this problem. Well, so the next step is add up all the electrical field. So we are taking a summation or taking an integration from minus infinite z to infinite z. And because we already we already what? We already separate this infinitely long line into infinite number of pair of sections above and below the horizon. So the integration can be carried out from z prime equals to 0 to infinity. So we're only taking the line integral on the top half. So we're taking the integral from 0 to infinity in terms in the z direction. So you're taking the integral over here. And this integration is a little bit complicated because you are taking the integration on the z prime. And here you have a z prime expression over here. So we shall introduce some tricks to dealing with this problem. So this is the first trick, right? Which can be referred as 变数代换吧，是不是？change of variable, right? So first, let's recognize this relationship. The distance is z prime. It's the coordinate, the coordinate on the z-axis. The distance on this way is r, and the angle of this triangle is alpha. So z prime over r is actually tangent alpha. Okay? So z prime equals to r tangent alpha. So here we are taking differentiate of z prime. So dz prime can be replaced with this, so which is equivalent taking the differential of r tangent alpha, that is r d alpha over cosine to the square of alpha. And cosine alpha can be represented with this, all right? So you need to go by the slides step by step at home, okay? So to recognize each step over here. So the other thing is to recognize this part which involves z prime. So r dz prime divided by this thing, and here you have cosine alpha to the square of this one. So you can substitute this part as d alpha. And the denominator becomes this thing, which can be further simplified as cosine alpha d alpha over r. 拜托，这回去要自己看一下，好不好？自己检查一下这个步骤。Okay. So this is referred to as the trick of technique of change of variable. So with change of variable method, the integration of z prime becomes integration of alpha. Therefore, the limit, the bound of the integration is changed into alpha equal to 0 degree and alpha equals to 90 degree. That is pi over 2. And the integral becomes cosine alpha d alpha. Okay? R is not relevant with alpha, so it can be pulled out of here. So the integration of this thing equals to, well, happens to be 1. So it's relatively simple, okay? So next, we have our result. That is an important result, okay? The electrical field set up by an infinitely long line charge equals to rho sub L0 divided by 2 pi epsilon 0 r AR. This result is important so that I need to write up on the board So let's discuss a little bit about the result. So we have a line source, infinitely long line source with a uniform line charge density, which is low sub-zero, low L sub-zero. And we have an observation point P over here. The distance from here, from the observation point to the line is R. Then what is the result? The field intensity is pointing towards this direction, and the magnitude is this. Can you recall the relationship of electrical field and charge density, that is the Coulomb's law? What are the difference of these two equations? This is point source, from a point source. This is from a line source. What are the difference? Well, they are related to material, right? This is the material property. They are proportional to the amount of charge. Well, they are true. Well, the larger the charge, the greater the electrical field. However, do you know that the relationship is somewhat different? For the point source, the magnitude is inversely proportional to the square of the distance, while for a line charge, the field magnitude is inversely proportional to the distance. Why? Because the dimension of the line source is growing from a point to a line. 所以它是一个什么维度的提升嘛？有没有？哦，从一个点变成一条线，所以它的影响力从 r 平方分之一变成 r 分之一，有没有？好 ，alright。啊，那个2拍跟4拍差在哪里？4拍是立体角了，2拍是一个圈圈的哦。所以其实那是跟几何结构有关的哈。OK 啊，所以课本在这边没有太多的讨论，但是之后我们会讨论了哈。所以 先留意一下这个变化，好不好？好 ，All right。well， 事实上课本也有讨论了哈。So in this slide we see that the magnitude becomes low sub L0 divided by 2 pi epsilon sub 0 r is everywhere radial to the line charge. So it's directing outwards as in a cylindrical fashion. So the reason why the denominator is 2 pi instead of 4 pi. For point charge, the electrical field is distributed like a sphere, while for a line charge, the electrical field distributed like a cylinder. 你可以把它想象成一个圆筒状一个牛奶桶圆筒状的一个对称所以称之为柱面的对称。Okay, so the next problem we like to deal with is related to example 1.7. Okay, well, we actually used the result of our previous solution, previous example. So let's move on to the calculation of electrical field from an infinitely large surface, a surface of extent to the infinite and beyond. Okay? So as you can guess, the dimension of this problem is upgrade again from into a two-dimensional source. So its surface extends everywhere. So how to do the problem? Remember, our principle is divide and conquer. So as long as we can divide it into small, simpler geometry, we can use the superposition law to find out the total field. So as the figure illustrates, the trick we will use here is to divide the surface into an infinite sum and collection of small and large circles. So we have an infinite number of circles of smaller and bigger radius. So the total field can be found by adding up the total contribution of these loops, circular loops. And here is the result we found in example 1.7. That is, for a loop of radius A, if the observation point is placed at a distance of z above this plane, the total field contributed by this circle will be this one. So what happens if we divide a surface into many small and large circles? That is, we shall find the total result by taking the summation in terms of what? In terms of A, with small a and larger a. So, the total, using the superposition law, the total field can be divided into the summation of total field from smaller circles and larger circles. So those circles are referred to as concentric rings. 同心啦，同一个中心 concentric rings, concentric loops. And each ring, each loop has a small width of dr, which suggests that in the next step we will take in the summation with respect of r. So, okay, so first is the expression for the charge. The total charge of the circular ring shall be the area of the ring and the charge density on that surface. So you see, the expression says low sub S0. S means surface. Low sub S0 means the surface charge density is uniform across the plane. So it's just a constant, low S0. And the area, which is the loop, the ring, will be the length, that is 2 pi r times the width, dr. So the denominator is this, okay? That is the total charge of the loop. And in the denominator is just adopt the expression over here, okay? So you have this thing. And you are taking the integration of this. So as this integrand suggests, we are taking the integration on the r direction R, and the limit is from R equals to 0 to infinity. So, unfortunately, we will use another numerical tool to solve this problem. 那第一章里头，其实常会遇到这种情况，就是要开外挂。OK， 好了，我尽量把那个外挂相关的那个数学工具列给你了啦。OK， 好，那这边其实也是啦，算是开外挂之一。它有点复杂啦，但多看几遍你就熟悉了。OK， right. Alright, so to do this integration, we need to identify this variable so that it can be dealt with using change of variable, right? Alright, so here we have r, dr, r to the square plus z to the square, and taking 3/2. So, well, what you need to do is practice, try differentiate this expression. Okay? Try practice differentiate this expression. It turns out if you do the differentiation, you will end up with this thing. Right? So this is the inverse of the differentiation. Okay? So this is kind of the integration of this thing is kind of this. Alright? Now. So the math is apply the bound to this expression, which is not that difficult. R equals to 0. When R equals to 0, here is just the magnitude of z. When R is infinite, this thing will approach to what? Approach to 1. Right? So so the result of this thing is 0 minus 1 over magnitude of z. And substitute it into the expression over here. It's end up as this. So z over magnitude of z give you either 1 or minus 1, depending on the polarity of z. If z is a positive number, then this is a positive sign, so which means the electrical field is pointing upwards if z is greater than 0. On the other hand, if z is smaller than 0, then this thing is minus 1, which means the direction of the electrical field is pointing downward. So this plot kind of suggests the solution of the two conditions depending on your position is above or below the surface. So if you have an infinite charge surface, the electrical field experienced from this surface, infinitely large surface charge becomes 2 epsilon sub 0 low as 0 the line charge density. That is, it's either positive or negative 1. And the implication or the significance of this result can be found by comparing this result with the other two cases. So comparing with infinitely long line charge, what are the difference, or what things are the same? Well, they are still subject to material property. You found epsilon sub 0. And they are proportional to the magnitude of charge. So here is low sub L0, low 1 is low sub S0. What are the difference? The distance doesn't matter, which means the electrical field produced by the influence of the electrical field produced by an infinitely large surface is no limit, has no limit. No matter you are close or away from the surface, you experience the same amount of electrical field. Is this a practical result? Do you find any application or any significance from this result? 你觉得这个答案实用吗？这个答案是什么？假如你有一个无限大的电荷表面，它所产生的电场是无远弗届的，不管你靠它近一点或靠它远一点，你感受到的电场是一样大的。听起来有点不现实，对不对？但其实你在电路学会找到一个跟这个很相关的一个状况哈。So think of this capacitor, parallel plate capacitor. So what is the field distribution in a parallel plate capacitor? Can you give me the, so suppose that the positive charge is on the top plate, the negative charge is on the bottom plate. What is the electrical field? Well, the electrical field is pointing from positive charge to negative charge. What is the geometric relationship about the electrical field established in the parallel plate capacitor? It's uniform. It's uniform. It's the same everywhere. No matter it is close to the top plate or close to the bottom plate, they experience the same amount of electrical field. So because for parallel plate capacitor, the surface area is relatively large toward the distance between the two plates. So it can be imagined as very large charged surface. So the field is uniform in this region. So you actually can find some synology in the study of capacitor, parallel plate capacitor. All right. So here is the more formal expression for the solution of infinitely large charged surfaces. So you can replace this as AN. That is the normal direction of the surface, depending that you are above or below the surface, right? So as you can see from the expression, the electrical field, the amount of electrical field is not perturbed by the position. It's not related to the distance from your observation point to the source surface. Okay. All right. So be sure to think of the derivation of today's example, because the four examples we have seen today are in fact closely related, okay? And I guess I can probably stop here, and we will continue for section 1.3.